Welcome back students to the video lecture series. I am Adil Mansoori from Civil Engineering Department of LJ Institute of Engineering and Technology. Okay students, so in the previous video we have already discussed about the activated sludge plants, its merits and demerits, then design consideration, and we have also completed the design numerical for activated sludge plant, right, wherein we have found out the hydraulic retention time, that is the aeration period, then food to microorganism ratio, then we also find out the efficiency, and lastly we found out the sludgeage in days. Okay, let us now move ahead with the new topic. Okay students, so let us now start with the next topic, that is the trickling filter. Okay, so on the screen you can see the pictorial representation of the trickling filter. So first of all, this process is known as attached growth process. Okay, wastewater enters through the central pipe and then enters the nozzle at the top of the tank. Okay, wastewater is sprayed onto the stone media through the nozzles, and the microbes present in wastewater attaches themselves to the stone media and grows and multiplies in number. Okay, now the layer of microbes attached to the stone is known as slime layer, and a particular time comes when the layer of microbes is so thick that the entire layer falls down along with the flow of wastewater. The removal of the layer from the stone media of these microbes of these microorganisms is known as sloughing of the slime layer. Okay, so let me explain you that you can see over here that there is one central pipe, right? So this will be the pipe which will carry wastewater from the primary sedimentation tank. Here there are rotary distributor column. There is a motor which here at the top, these are four pipes, right? So these will be rotating in this direction. Okay, these are rotating. So each and every point over here, you get some of the water is sprinkled. Okay, these are the stone layers. You can see over here, these are the stone layers, right, and these are the perforated walls, lateral walls. Clear? So students, you can see over here, so there will be a stone like this. Okay, and the layers, the wastewater which is trickled over these layers, right, layers of stone, what will happen is the microbes will attach to this surface. They will multiply and grow in numbers, right, and then when the layer becomes very large, or the thick layer when it becomes, what happens is it will flow along with the flow of the water coming from the top, right? So this layer or removal of this layer is known as sloughing of slime layer. Okay students, so I hope this trickling filter is clear to you. You can see over here that this is the central pipe, right? Clear? And these are four pipelines with perforations so that water is sprinkled over here, right? This is the stone media, right? And this is rotating one, right? So it will be sprinkled all over the circular area. Clear students? So let us now talk about the types of trickling filter. There are two types of trickling filter, that is the conventional type trickling filter and high rate trickling filter. Okay, So what is the difference between high rate trickling filter and the conventional trickling filter? So when entire amount or some part of wastewater is circulated back into the trickling filter, it is known as high rate trickling filter. Okay. So next is, what is the advantages of recirculation? So first one is, high loading rate increases sloughing of microbial layer, that is slime layer. Then odor problem is reduced. Nozzles run continuously, that is water is continuously sprinkled over the entire trickling filter area, and efficiency of filter is as a result increased. Okay, so let us now have a look at some of the important terms. First one is known as hydraulic loading rate. It is the discharge per unit plant area of the filter. Okay, it is the unit of hydraulic loading rate is million liters per day per hectare. Okay, then the organic loading rate, it is the kg of biochemical oxygen demand applied per day per unit volume of the filter, that is in kg per day per hectare meter. Okay, then recirculation. So what is recirculation? As I said, a part or whole discharge of wastewater is sent back to the upstream. Okay, and recirculation ratio is nothing but the ratio of R by I, where R is the wastewater which is recirculated discharge and I is the raw wastewater discharge. Okay, that is R is the recirculated wastewater discharge and I is the raw wastewater discharge. Clear? So let us now have a look at another topic, that is difference between conventional and high rate trickling filter. So the first column indicates parameter, then the conventional trickling filter data and high rate trickling filter data. So the hydraulic loading rate for conventional trickling filter is 20 to 40 million liters per day per hectare. Okay, whereas in case of high rate trickling filter is in between 110 to 330 million liters per hectare per day. Okay, talking about organic loading is in between 900 to 2200 kg per day per hectare meter, whereas in case of high rate trickling filter it is in between 6000 to 18000 kg per day per hectare meter. Okay, depth of filter of a conventional trickling filter is between 1.6 meter to 2.5 meters, and that of high rate trickling filter is between 1.2 to 1.8 meters. Dosing interval is 5 to 10 minutes for conventional trickling filter, and it should not be greater than 15 seconds for high rate trickling filter. Okay, talking about quality of secondary sludge is usually black and oxidized for conventional trickling filter, but in high rate trickling filter the secondary sludge is black but it is not oxidized. And we know that HRTF needs recirculation, whereas conventional trickling filter do not need circulation. Okay, so next is merits of trickling filter. So their working is simple and skill supervision is not needed. Okay, they have very high organic loading rate. It means size of the filter are less. They remove 80% of suspended solid and 75% of BOD5 from its influent. They are flexible in operation. and can withstand high organic loading, and sometimes also shock loading can be withstood. Okay, they are self-cleansing unit. So trickled water falling on stone and increasing thickness of biofilms are responsible for sloughing of films. Okay, then mechanical wear and tear is less as they contain less mechanical equipments. Nowadays, plastic pipes can be employed, which would eliminate corrosion problems. Okay, so these are the some of the merits of trickling filter. Let us talk about the demerits of the trickling filter. So the first one is the head loss through this filter is very high. Construction cost is high. Then these filters cannot treat raw wastewater. These filters These filters cannot treat raw wastewater and primary sedimentation tank is must. Trickling filter creates several operational troubles. For example, fly nuisance. Fly named Psychoda is developed which may create problems on reaching the residential area. The problems can be controlled by flooding filter for 24 hours and the flooding will destroy the larvae, but in doing so the operation of filter is disturbed. So to avoid this situation, a standby unit is always provided in plant so that it can be used for wastewater treatment at the time of flooding. Okay. Next problem is odor nuisance. Odors generally do not prevail in trickling filters where rotary distributors are provided. But if fixed nozzles are provided, then hydrogen sulfide generation creates problem. In these circumstances, wastewater may be chlorinated. Then the third problem is the ponding trouble. Third problem is the ponding trouble. Ponding trouble when filter media is clogged, the flooding occurs. Right? So when you sprinkle the wastewater on the filter media, then when it gets clogged and when you go on sprinkling the wastewater, then the flooding occurs. This is due to heavy growth of algae and fungi, and algae can be controlled by adding copper sulfate and keeping the medium wet with copper sulfate containing wastewater. Fungi can be killed by chlorination of wastewater. Okay, so these are some of the demerits of the trickling. Okay students, so let us now start with the next topic, that is the difference between the trickling filter and activated sludge plant. Okay, so the first difference between the trickling filter and activated sludge plant is related to bacterial growth. Okay, so the bacteria usually grow on the surface of stones in case of trickling filter, whereas in case of activated sludge plant, bacteria grow in wastewater which are in suspension. Okay, uh, trickling filter has efficiency of BOD removal of up to 70 to 80%, whereas activated sludge plant has BOD removal efficiency of 90%. The initial cost of trickling filter is high, whereas the initial cost of activated sludge plant is low. Okay, skilled workers are not needed in case of trickling filter, whereas skilled workers are needed. Sorry. Skilled workers are needed in case of trickling filter, whereas skilled workers are not needed in case of activated sludge plant. It is used when so trickling filter is used when wastewater discharge is high, and activated sludge plant is used when wastewater discharge is less. Okay, there is no dark layer foam layer formed on trickling filter, whereas dark foam layer is formed in case of activated sludge plant. Aeration is not required in case of trickling filter, whereas activated sludge plant it is mandatory. Okay, so let us move towards the next topic. So the next topic is the design step of high rate trickling filter. Okay, so the first step that involved in the HRTF design is to find the BOD of the influent in kg per day. Okay, that is biochemical oxygen demand of the wastewater that is coming out of the primary sedimentation tank and which is entered into trickling filter. Then particular BOD of that influent is needed in kg per day. Okay, step 2 involves assumption of BOD removed in primary sedimentation tank and remaining entering the HRTF. Okay, that is certain percent of BOD is usually removed in case of primary sedimentation tank, right? So rest of the BOD will enter into the trickling filter, right? So we have to make the assumption of that. Step 3 involves BOD of effluent in kg per day, right? That is after the treatment is complete, whatever the wastewater is coming out of the trickling filter, that is known as effluent, and we need to find out the biochemical oxygen demand of the effluent as well. Okay, step 4 involves to find out the efficiency of the filter. Okay, next is to find out the recirculation ratio. Step 6 involves assumption of depth. Then next step is to find out area, and from area we can find out the diameter of the high rate trickling filter. Okay, so I hope these design steps are clear in your mind. Let us move ahead. We are now heading towards the numerical. So let us have a look at the numerical. Design a high rate trickling filter for a flow of 4.5 mld if recirculation ratio is 1.5. BOD of wastewater they have given is 250 milligram per liter, and final effluent that is desired is 30 milligram per liter. Okay, we need to assume the suitable data. Okay students, so let us now start with the solution. Okay, now what they have given is the flow of wastewater. Okay, so they have given discharge equals to 4.5 mld. Okay, then they have given the BOD of wastewater, right? BOD of wastewater, so that is BOD influent. Okay, they have given us 250 milligram per liter, right? Then they have given effluent, so BOD effluent equals to 30 milligram per liter, right? Now they have also given recirculation ratio R by I equals to 1.5. Okay, so now the first step that is involved is to find out BOD of wastewater in kg per day. Okay, so first thing that is there is that in 1 liter 250 milligram of BOD is present. So how much BOD will be present in 4.5 mld of wastewater, right? So I am writing over here BOD present in wastewater, right? So this will be equals to 4.5 into 10 to the power 6. I am converting it into liter per day, right? And since it has 250 milligram per liter, right? So multiplying with 250. Okay, so this will be equals to 1125 into 10 to the power 6 into 10 to the power minus 6 kg per day, right? Why kg per day? Because multiplying 250 with 4.5, it will yield you 1125, right? 10 raised to 6 as it is, but this will be in milligram per day, right? So after converting into, so converting milligram into kg, I have multiplied with 10 is to minus 6. Okay, so this will be equals to 1125 kg per day, right? Now next step is to assume BOD removal in primary sedimentation tank. So assume BOD removal in PST, that is equals to 30%, say. Okay, so therefore can I say that BOD entering HRTF will be equals to 70%, right? So that will be equals to 0.70 into 1125, that will be equals to 787.5. So that will be equals to 787.5 kg per day. Understood, students? So what we did is, first we have found out they have given us discharge, so we found out total BOD present in the total discharge, right? And assuming that 30% of BOD is removed in primary sedimentation tank, we are calculating the BOD that is entering in high rate trickling filter. Okay, so next, to find out BOD of effluent. Okay, next step is to find out BOD of effluent. Okay, how much is desired? It is desired is 30 milligram per liter, right? So therefore we know that the quantity of wastewater that is entering the trickling filter will be removed, will be the that quantity only that will be removed, right? That is, once whatever the quantity of wastewater is entering the trickling filter, the same quantity has to be removed, right? So can I say that BOD of, therefore BOD of effluent in total wastewater, right? So this will be equals to 30 milligram per liter into 4.5 mld. So this will be equals to 4.5 into 10 to the power 6 into 30 into 10 to the power minus 6, right? And that will be in kg per day, right? So this will be equals to 135 kg per day. So it means that whatever the wastewater, that is 4.5 mld, so this means that when 4.5 mld of wastewater is entering the trickling filter, right, it will have 787.5 kg per day of BOD, and when it will be removed from the trickling filter throughout the day, then it will have total BOD of 135 kg. Understood? So now can we find out the efficiency, right? So therefore BOD removal efficiency, right, eta will be equals to BOD influent minus BOD effluent, right, upon BOD influent multiplied by 100. So this is the formula, right? So what is BOD that is entering? 787.5. What is that is left behind? 135 divided by 787.5 multiplied by 100. So this will be equals to 82.85 percentage. It means that the trickling filter removes 82.85% of BOD. Understood? Okay, students. So next step, they have given R by I, right? So I am writing recirculation ratio 1.5, right? That is the thing, but R by I. Now the recirculation factor, we need to find out recirculation factor. Okay, so recirculation factor F will be equals to 1 plus R by I upon 1 plus 0.1 into R by I whole square. Okay, so this is known as recirculation factor. Clear? So this will be equals to F will be equals to 1 plus 1.5 upon 1 plus 0.1 into 1.5 the whole square. Okay, so this will be equals to 1.89. Clear? Now there is one crucial step which you should remember. Okay, so next is we need to find out the volume. Okay, so for that we will be using equation of efficiency. So equation of efficiency is 1 upon 1 plus 0.0044 under root y by vf. Okay, so efficiency we know how much it is. We have found out 82.85 percentage, right? Divide into 100 divided by 1 plus 0.0044 under root of y is the BOD influent, that is 787.5, divided by volume, that is we have to find out, and recirculation factor, that is 1.89. You have to be very careful because in this formula volume is in hectare-meter. Okay, so after simplification you will get value as this. Okay, that is 1882.8 into 10 to the power minus 4 hectare meter. Okay, now we know that 1 hectare equals to 10 to the power 4 meter square. So I am keep placing this value over here. So this will be equals to 1882.8 into 10 to the power minus 4 into 10 to the power plus 4 into meter cube, right? So this will be equals to 1882.8 meter cube. Clear? So we have found out the volume. Next step is to find out the area. So for that, assume depth equals to 1.5. So therefore area will be volume by depth, that is 1882.5 divided by 1882.8 divided by 1.5. So this will be equals to 1255.21 meter square. Okay, so we have found out the area. So from this we can find out the diameter. Okay, so area is given, area we found out as area equals to 1255.21 meter square, right? So therefore 1255.21 equals to pi by 4 into d square, right? So therefore d will be equals to 39.47 meter. So we can say that provide diameter equals to 40 meter. Clear? So final answer is that provide a HRTF with 40 meter diameter, comma 1.5 meter depth and recirculation ratio 1.5. So here we complete our numerical for high rate trickling filter. I hope you must have understood. Okay students, so let us now start with the next topic, that is sludge digester. Okay, so this process is an anaerobic suspended growth process. In wastewater treatment plant, we are already providing primary and secondary sedimentation tank. From the bottom hopper of the primary and secondary sedimentation tanks, sludge is transported to the sludge digester unit. Okay, that is the unit that we are studying. Okay, the function of the sludge digester is to convert the solids of the sludge into simpler bio non-degradable solids under anaerobic conditions. The function of the sludge digester is to convert the solids of the sludge into simpler bio non-degradable solids under anaerobic condition. As the sludge digester deals with the primary and secondary sludge, it is also known as sludge treatment unit. The primary and secondary sludge have different characteristics. Okay, so I will show you the picture, right? So dear students, you can see that this is the schematic diagram of sludge digester. Okay, so from the primary and secondary sedimentation tank, the sludge is entering from this side. Okay, so it will enter into this tank. Okay, now this is an anaerobic condition, right? So here on the top there is a truss roof. Okay, and there is a dome provided. This dome is for collection of the gas that is being generated. Okay, now you can see that after the process is complete, the digested sludge is settled at the bottom, which is removed. Okay, and whatever the supernatant liquid is there, okay, that is the effluent, that will be removed from this sides. Okay, now the gas which is collected, being lighter than air, it will get collected in the gas dome. Okay, and it will be removed with the help of sludge gas pipeline. Understood students? So Let me explain you the whole process. So in this math in this So, in this method, saprophytic bacteria are present. They carry degradation first and form intermediate product of volatile acids, and then there are methane forming bacteria which convert acids into carbon dioxide and methane. Okay, so first what happens is there are saprophytic bacteria which convert the waste into intermediate product of volatile acids, and then there are methane forming bacteria which convert those volatile acids into carbon dioxide and methane. Okay, low molecular weight fatty acids are the intermediate product of anaerobic biodegradation, and these acids are known as volatile acids because they can be distilled at atmospheric pressure. Okay, acetic acid, propionic acid, butyric acid, and up to certain extent valeric acid or isovaleric acid or caproic acids are the important components of the anaerobic biodegradation. Saprophytic and methane formers work simultaneously. So saprophytic produce volatile acids and methane formers produce methane. Fine. It should be noted that the methane formers are sensitive to pH value, and if their population is not sufficient, then methane formation process, that is the degradation of volatile acids by them, will be at a slower rate, right? And at the other side, saprophytic bacteria will continue producing volatile acids at a faster rate. So because of this, there will be decrease in pH value due to accumulation of volatile acids. So this hampers the growth of methane formers and consequently formation of methane. Okay, so normally the volatile solids concentration between 50 to 250 milligram per liter expressed as acetic acid is indicating good or healthy condition in anaerobic system. Okay, so at a standard temperature and pressure, 1 kg of ultimate BOD of or 1 kg of COD removed by anaerobic digestion yields about 0.35 meter cube of methane gas. And in terms of population equivalent, gas production may be 20 to 25 liters per capita per day. Okay. So you can see in the picture there is a graph showing methane gas production versus temperature. So it is clear that in mesophilic region, right, that is the first region between 20 to 40 degrees centigrade, 45 degrees centigrade, the temperature of 35 degrees centigrade is corresponding to the minimum digestion time. Okay, so it is corresponding to the minimum digestion time, where as in thermophilic region 55 degree temperature is the temperature corresponding to the minimum time of digestion. Okay, so this is a graph of temperature versus time of digestion in days, right? So you can see that a production of gas varies with temperature and is zero point 0.4 to 0.45 meter cube per kg of volatile solids added, or 0.45 to 0.9 meter cube of per kg of volatile solids digested. Okay, so production of gas varies with temperature and is zero point 0.4 to 0.45 meter cube per kg of volatile solids added, or 0.45 to 0.9 meter cube per kg of volatile solids digested. The calorific value of the gas produced is 4000 to 5000 kilocalorie per meter cube, and the heat of content of methane gas is 8800 kilocalorie per meter cube. Okay, so these are just the informations. Okay students, so let us now start with the next topic, that is difference between primary sludge and secondary sludge. So as you can see on the screen that the moisture content of the primary sludge is 95%. Okay, and in case of secondary sludge, if the sludge is coming out of the activated sludge plant, it will contain 99% of the moisture content, whereas in case of trickling filter it is 95 to 98%. Okay, primary sludge is highly putrescible. Okay, and secondary sludge is not highly putrescible. Fine. Talking about the quantity of wastewater generated, then it is 20 meter cube per million liter of wastewater. That is, if I talk about the quantity of primary sludge, then in case of primary sludge, okay, so primary sludge is removed, or the quantity of the primary sludge generated is 20 meter cube per million liter of wastewater, and in case of trickling filter, that is the secondary sludge quantity is 5 meter cube per million liter, and if the secondary sludge is coming out of activated sludge plant, then the quantity of secondary sludge is in between 35 to 50 meter cube per million liter. Okay, now the primary sludge contains volatile solids of 70%, whereas secondary sludge contain volatile solids of 45 to 70%. Okay, so let us now talk about the operational efficiency of sludge digestion. Operational efficiency of sludge digestion depends on various factors. For example, pH should be in between 6.7 and 7.5. The alkalinity of these wastewater should be in between 1000 to 5000 milligram per liter of calcium carbonate. Volatile acids are less than or equals to 250 milligram per liter. Okay, then nitrogen and phosphorus availability is necessary in case of sludge digestion. Recycling of digested sludge improves efficiency. Okay, so let us now move towards the next topic, that is the design criteria of the sludge digester. So the volatile solids loading should be in between 0.25 to 1 kg per meter cube per day. Okay, then retention times should be between 20 to 60 days. Digester volume is found out by this formula, that is Vf minus 2/3 of Vf minus Vd into capital T, where Vf is the volume of fresh sludge, Vd is the volume of digested sludge, and T is the digestion time in days. Okay, so let us now move towards the steps of the sludge digester. So the first step is to assume that 65% solids are removed in primary sedimentation tank. Also assume that moisture content of the fresh sludge is 95%, and assume 5 kg of dry sludge make 100 kg of wet sludge. Okay, the next step is to find the density of sludge. Then step 5 includes finding out the volume of the fresh sludge, and step 6 includes finding out volume of the digested sludge. Then assume the retention period of 30 days, then find the volume of digester. From the volume of digester, you can provide 6 meter depth and find out area, and from area you can find out the diameter. Okay, so let us now move towards the numerical. So the data says that design a sludge digester with the following data. That is, average sewage flow they have given is 50 into 10 to the power 6 liter per day, that is 50 million liters per day. That is 50 million liters per day. Then total suspended solids are 300 milligram per liter, and moisture content of the digested sludge is 85%. Okay, and they are saying that assume the other data. Okay, so let us now start with the numerical. Okay, so let us now start with the solution. Okay, so first thing we need to find out is the mass of suspended solids. Okay, so we know that total suspended solid is 300 milligram per liter and total quantity of wastewater is 50 million liters, right? So first thing that we need to find out is the mass of suspended solid in wastewater generated, right? So this will be equals to 300 milligram per liter multiplied by 50 into 10 to the power 6 liters per day, right? So this will be equals to 15,000 into 10 to the power 6 milligram per day. So I will convert this milligram into kg. So that will be equals to 15,000 into 10 to the power 6 into 10 to the power minus 6 kg per day, right? So this will be equals to 15,000 kg per day, right? So in 50 million liter of wastewater, total suspended solid content is 15,000 kg for 1 day, right? Now next step is to assume 65% of solids are removed in PST, right? So assuming 65% of solids removed in PST. Okay, so mass of solids removed in PST will be equals to 0.65 into 15,000. So that will be equals to 9750 kg per day, right? So total suspended solid is 15,000 kg, out of which 0.65% is removed in primary sedimentation tank, right? So how much it will go into sludge digester? Remaining 35%, right? So mass of these solid removed in PST is 9,750 kg. Okay, now we need to assume 5 kg of dry sludge make 100 kg of wet sludge, right? So therefore 9,750 kg of dry sludge will make how many kg? So this will be equals to 100 into 9750 divided by 5, and that will be equals to 1,95,000 kg of wet sludge per day, right? So what is the fundamental? That is 5 kg of dry sludge make 100 kg of wet sludge. Then this much suspended solid which are already removed will make how much wet sludge? So multiply by 100 and divide by 5, right? So that will be the total quantity of wet sludge produced per day. Okay. Next, find out the density of sludge. So for that we need to assume specific gravity 1.02, right? So unless mentioned you will take this, right? So density of sludge, or sorry, specific gravity will be density of sludge by density of water, right? So therefore 1.02 into 1000, that is equals to density of sludge. So therefore density of sludge will be equals to 1020, right? That will be in kg per meter cube. Agree? Okay. Next thing that we have to find out is the volume of raw sludge produced. So volume of raw sludge produced, that is Vf, will be equals to mass by density, right? So this is 1,95,000 divided by 1020, that is equals to 191.17 meter cube per day, right? So this will be the volume of raw sludge that will be produced. Okay. Now we need to find out the volume of digested sludge, right? So volume of digested sludge at 85% moisture content and moisture of fresh sludge equals to 95%. So therefore Vd, that will be equals to Vf 100 minus P1 upon 100 minus P2. So this is the equation of finding out the digested sludge, right? Where P1 is the moisture content of fresh sludge and P2 is the moisture content of digested sludge. Okay. So this will be equals to volume of fresh sludge, we know 191.17, right? 100 minus 95 divided by 100 minus 85. So this will be equals to 63.72 meter cube per day. Okay. So volume of digested sludge we have found out equals to 63.72 meter cube per day. Okay. Now we need to find out the volume of tank, right? So for that, assume detention time equals to 30 days. Okay. So therefore capacity of tank will be equals to V equals to Vf V will be equals to Vf minus 2/3 Vf minus Vd into T, right? So this was the equation. So this will be equals to, what is the value of fresh sludge? 191.17 minus 2/3 191.17 minus digested sludge 63.72, assuming for 30 days, right? So this will be equals to 3186.1 meter cube. So this will be the volume of the tank, right students? Now once you have found out the volume, assume depth and find out the area and the diameter. So provide 6 meter depth for cylindrical tank, right? So therefore area will be equals to 3186.1 divided by 6, that is V by D, right? So this will be equals to 531.0 meter square, right? So area is usually pi by 4d square, right, for cylindrical, for circular area, right? So therefore D will be equals to 26 meters. Fine. So therefore you can write, therefore provide a sludge digester with dia equals to 26 meter and depth equals to 6 meter. So this will be your final answer. Okay, so that's all for today's video. We will be seeing some new topics in the next video.